All right. Good morning, everyone. So let's see. So there's a question in the chat to say when our grades for the last exam will be in. I yeah. So I grade one section of the class. So the for you guys took the exam on Monday. I'll probably grade them some point today, and then when I finish grading, I will then put your grades in on Moodle. So expect sometime today, okay? Probably in the afternoon you'll see that. Okay. Um, so let's get started with a couple reminder items here, a few reminder items here. So homework number 10 is actually due tomorrow by midnight, okay? Some of you guys probably thought it was due last night, but this time it's due on tomorrow on Thursday. And then the last two homework assignments, they are extra credits to them. Will be due on Saturday and Monday. Okay, so each are like 2 weeks apart from the previous one. So make sure you can also finish them because they will be giving you extra credit for to your final grades, and then the problems in them, the content covered for the problems in them will be also in the final exam. Okay, so make sure you actually at least finish as much as you can. I know it's getting tight, but also, if you didn't get a chance, make sure you study the solution afterward, okay? All right. Also, for this week, this Wednesday, Friday, and then next Wednesday, they are designed for makeup labs. So if you have any missing labs, you can come in to make them up. If you are in Friday's section, you can also come in the Wednesday section, okay, if your time permits. So, and then likewise, so if you want to make up more than one lab, you can go to Friday section if that's allowed for you if you are in the Wednesday section. Okay. So for the final exam, currently the plan is to have Wednesday's lab attendee taking on Wednesday during the lecture, and then the Friday lab attendees will take that as scheduled from by the university on Friday next week. Okay, early time at 7:50. All right. Um, Now there's might be chances that we are going remotely complete in the next few days because the numbers of positive cases are been increasing. So um, the university hasn't decided that yet, but in case that's what we decide going to do for the remote learning, then both Wednesday and Friday lab attendees will take the exam at the same time. Okay, so if that happens, all right. And also the last reminder item will be the end of course survey. So if you get a chance, anytime in next a few days, you are encouraged to finish the surveys, okay? To in just that we can improve this class. Okay. Let me see the chat here. Um, Yes, so if you don't have any missing labs, you don't have to come for the labs. Okay, so totally you should have 10 labs done by right now. So, and that will be it for the semester. Okay. And then there's a question also, can we make out both labs in one day? So yeah, it's possible if you can finish them by 5:30 in the afternoon, then you can do that. You can try to do that, okay? Or you can try to maybe just finish parts of the lab on one lab, and then if your time ends, then we can do on Friday or coming another day, okay? Um, Another question is about the final be so pretty much it's a final cumulative or just the having emphasized for the past a few chapters. So yeah, so it will be just we will just cover the content in the last a few chapters. So it's from chapter 10, 11, 12, and then we kind of jump to chapter 16. Okay, so those will be the chapters covered. But yeah, I would say always say physics exams are cumulative because you always use the knowledge you learned earlier from time to time. Okay, but that will be the emphasis for those chapters. All right. So let me see what else. I think that's it for the chat. Okay. Um, so we'll probably get started for chapter 12. Chapter 11, I covered in the asynchronous lecture recorded online. So if you haven't get a chance to watch that video, make sure you watch them at some time. Okay, so it's a actually relative short video. I think it's only like a little bit over 30 minutes. Okay, so find some time and then watch the video. So this is continuing from chapter 11. So in chapter 11, we talk about fluid statics. Okay, so that means we are interested in the physics of the static fluid when the fluid is not moving actually. Okay, but in this case, in this chapter, we'll be looking at the dynamics of the fluid. Okay, so that means the fluid is actually floating, flowing. Okay, so let's see. So the first thing we want to take a look at the flow rate. So if fluid is flowing, then we want to know that how much fluid is flowing from one location or through one point at one particular location through this point P. Okay, so that's defined as flow rate. It's the volume of the fluid per unit time. Okay, flowing past the point through area A. Okay, so it's referring to the volume. So given 1 second, how much volume of the fluid passing through here. So if you haven't watched the video of last lecture, so fluid, anything that is liquid or gas, they are considered as fluid. Okay, so both gas and liquid, they are considered fluid, and solid is another subject. Okay, so flow rate, because it's defined as the volume divided by time t. Okay, so then it should have SI unit of meters cube over second. Okay, so in this figure, you might be paying extra attention with the notation. So capital V stands for volume. Small v with a bar, that means the velocity, the average velocity. Okay, the velocity of the flow of the fluid. Okay, and Q will be the flow rate. A will be the cross-sectional area. Okay, D will be the distance. So velocity equals to distance over T. Okay, and then in that sense, Q equals to V over T, or equals to A times D, because volume in this case, and the cylindrical volume will be equal to the cross-sectional area times the length D. Okay, and D divided by T will give you average velocity. So then flow rate could be also calculated as the cross-sectional area times the average velocity of the fluid. Okay. All right. Now, if you look at a stream that has water, so then the amount of water comes in from the upper stream should be equal to the amount of water comes out at the lower stream. Okay, so that's called the continuity of the fluid, or we can call it mass conservation, because mass coming in should be equal to mass coming out. Okay, so the same mass comes in equals to the same mass goes out, or the same volume of water comes in equals to the same of the water goes out. Okay, so with that, then we can see, so for per unit time, so then the volume comes in per unit time should be referred to the flow rate of Q. Okay, so that in that sense, that means the Q should be constant. Okay, so VA times Q is going to be equal to constant, because flow rate should be constant. Okay, from the upper stream to the lower stream or the downstream. So in that case, then you can write V1, the average velocity of the velocity times A1, should be equal to A2 times V2. Again, this should be the continuity of flow, right? So because the volume comes in should be equal to the volume comes out, or volume at one point through one point should be equal to volume goes through at the other point or the second point. Okay. All right. So let's take a look a quick example here. So this says the Waikato Falls on the um, Waikato River. I'm not sure about my pronunciation, but let's just take it. It's one of the New Zealand's most visited natural tourist attraction. On average, the river has a flow rate of about 300,000 liters per second. Okay, so this is in liters per second. You might want to convert into meters cube. 1,000 liter is equal to 1 meters cube. Okay, that's the conversion factor. It says at the gorge, the river narrows to 20 meters wide and averages 20 meters deep. What's the average speed of the river in the gorge? And then what's the average speed of the water in the river downstream of the falls when it widens to 60 meters by 40 meters? Okay, the depth is will be 40 meters. Okay, so on this one, you can pretty much apply Q will be the flow rate equal to the speed times the cross-sectional area. Okay, so you can go ahead and then do that. And then you might also apply like a V1 A1 equals to V2 A2. Okay, so for part A, you probably just use that one. For part B, you can apply this one or you can apply that one a second time. So either way. Okay, so I'll give you guys a couple minutes and then we can take a look on the solution together. All right, so let's take a look here. So it actually tells us the Q is 300,000 liters, okay, per second. So you can convert that into 300 meters cube per second to be the SI unit, okay? It tells you at one point at the gauge here, it's 20 by 20, so then that will give you the area, it will be 20 meters by 20 meters, okay? So you're looking for V at the gauge should be just equal to Q over A, will be the 300 meters cube per second divided by 20 meters times 20 meters, okay? So this should be straightforward. It's going to be 0.75 meters per second. Okay, but let me just pull out my note to make sure. So 0.75 meters per second. Okay, on the first one here. On the second one here, so you can apply this time one more time. Just the area changes. The Q will be the same because at the downstream, the flow rate should be the same as the upstream. Okay, so that shouldn't change. So that's because continuity of flow. So you can apply this one more time. So you can do again V equals to Q over A. This time, the Q stays the same, but A changes to 60 meters by 40 meters. Okay, so 60 by 40, that will give you 0.125 meters per second. Okay, or you can use that one, just set up the flow continuity here. So V1A1 equals to V2A2. Okay, in that case, then you're looking for V2. V2 should be equal to V1A1 divided by A2. Okay, so it will be the 0.75 will be the V1, and then A1 will be the 20 meters by 20 meters. Okay, divided by A2 here, divided by A2, that's 60 meters by 40 meters. Okay, that should also give you 0.125 meters per second. So just a second method on this one. Okay. You can let me know if you have questions. I will pause for a few seconds. Okay. All right. So if you are clear, we can check on the next section on Bernoulli's equation. So basically, we know that at one location, this amount of the fluid, okay, goes through point one as equal to the amount of fluid going through a second location at point two over here, okay? So the mass, if you look at this one, if volume is the same, then mass will be the same, right? So we can take this amount of the fluid, the mass to be M1, or just M, because M1 will be equal to M2. So they are both M, okay, it doesn't matter. So the second one should be also M. Now you can see at one point, this amount of fluid going to point one. Now time t later, it will go to point two, okay? So then we are talking about the same water here. This part and then that part, they are the same part actually, just in different times, okay? So you can see here, if this is A1 V1 and this is A2 V2, so you can see A2 actually narrows down, so it decreases, then V2 increase, right? So you can see the same amount of water at one point as having V1 as velocity, and then at the second time, at the narrow part of the stream is having V2 a larger speed. So that means the kinetic energy actually increases, right, for the water at this location compared to at some time later at point two, right? And then that should be equal to net work done by down on the water. Okay, so there's net work done by on that water. So what's actually doing this work over here? All right, it turns out that it's actually the pressure difference over here from at this point and that point. Okay, so that gives you the driving force for this guy to go from here to there. Okay, so work will be done as a result of pressure difference there. Okay, and it turns out that there's a relationship between pressure and velocity in the fluid. Okay, so that relationship is called Bernoulli's equation. So basically, it says the pressure plus 1/2 rho V square plus rho GH equals to constant. Okay, so those three quantities, so pressure and velocity are also involved, and then in additional, there's another the height of the water of the fluid is also increased. So this actually is the potential energy, gravitational potential energy, but we should refer to as potential gravitational potential energy density. Okay, so because we are using density over here. Anyway, so those three quantities should add up to be zero, and then it was proposed by Daniel Bernoulli um, a, a few hundred years ago. Okay, so and you can also express this in another mathematical form. So taking two locations in the fluid. So if the fluid goes from one location to a second location, okay, so then P1 plus 1/2 V1 square plus rho GH1 should be equal to P2 plus 1/2 rho V square plus rho GH2. Okay, so they should equal to each other, meaning initial should equal to final, or at one location should equal to the other location. Okay. We'll take a look on the applications of the Bernoulli's equation. So first, you guys might have experienced this. So if you are driving by a truck, okay, so if truck goes in one direction, and then so this effect will be more significant if you are going in the opposite direction of the truck. Okay, so you'll see that you kind of you might, I don't know if you are inside a car you can feel, but because in between the car and the truck over here, so the velocity or relative velocity, okay, will be larger than the velocity of the fluid over here on the two sides. Okay, so then pressure, because P, if you look at Bernoulli's equation, so let me write it here. We are going to refer this a few times. P1 plus 1/2 rho V1 square plus rho GH1, that should be equal to P2 plus 1/2 rho V2 square plus rho GH2. Okay, in this case, your vertical location H1, H2 are the same. So for the car and the truck, they are the same. So then this Bernoulli's equation reduced to two terms on each side. So one rho 1 plus P1 plus 1/2 rho V1 square equals to P2 plus 1/2 rho V2 square. Okay, so on the side, if you have V1, if this is larger than this guy, then this has to be small, right? If this is large, then this should be small, okay? So if velocity will be large, then the pressure will be small, okay? So if you are in the direction opposite to the truck, then relative speed of the fluid inside here should be larger, so then pressure here will be small. Then pressure on here should be larger, okay? So that's the pressure difference. Now, if you are getting too close to the truck, you will feel that, okay, even more. So then there's actually pressure difference on this side to that side. So you kind of feel like you're pushing towards that guy, okay? Or if you are, imagine if you are standing on the roadside and then a car or a truck goes by quickly, then you probably will feel that there's a force pushing you towards the car. So that will be very dangerous, okay? So this is one of the application of Bernoulli's equation. And then the second example showing here in the figure, you can also, I think you can see this often in the highway. So, so if a truck with a tarpaulin on the top, if it's moving with a certain speed, then you will see this actually bulges outward. Okay, so it kind of like goes in that way, because then on the top here, the air as the fluid here has larger speed, then the pressure will be smaller than underneath the tarpaulin. Okay, because underneath the tarpaulin, the fluid should have relative small speed, so pressure will be larger. So then it's pushed upward. Okay, when it's stationary, it will appear to be just flat because there's no significant pressure difference. Okay. All right. Another application for Bernoulli's equation, we can take a look. Actually, it will apply also to static fluid. Okay, so in that case, then the velocity v1, v2 will be just equal to 0. Then the Bernoulli's equation again reduces to two terms on each side. So on one side will be just P1 plus rho g H1. The 1/2 rho v square term will disappear because velocity equal to 0. Okay, and then the same to the other side of the equation. So this is in the previous chapter. You can see actually, so that's where the buoyant force is coming from. Okay, so because of the pressure difference from the top and the bottom here, because you are at two different locations. If you are at the above higher location here, then pressure should be small, and the bottom here, a deeper location H2 here, then this guy will be larger. Okay. So that gives you the buoyant force. All right. We can take a closer look on the when the two vertical locations are the same, H1 equal to H2. Again, you will have two terms on both sides of equation. So P1 plus 1/2 rho V1 square equals to P2 plus 1/2 rho V2 square. This is all called the Bernoulli's principle. Okay. We actually apply Bernoulli's principle very often in our daily life. Okay, so one of the example would be the airplane when it's flying in air. So that's utilizing Bernoulli's principle. Okay, so the design of the wings of the airplane, it's rather flat at the bottom here, but it curves up on the top. Okay, so then for the air goes through the bottom wing here because in the same time period, it will travel less distance than the air that goes through the top of the wing because it curved up. Okay, so then the velocity at the top of the wing is larger for the air than the velocity at the bottom of the wing here. Okay, so you have larger V on the top here. That means you will have less pressure on the top than the bottom, right? So the top have less pressure, the bottom will have higher pressure because the velocity at the bottom is smaller. So then there's a difference in the pressure from the top of the wing and then the bottom of the wing that gives the lift on the wing, okay, for the airplane, okay. And in order to achieve enough lift, then the speed should be relatively larger, okay. So that's why the airplane are traveling at larger speed, okay. All right. There are also other applications of Bernoulli's principle in our daily life. So for example, the Bunsen burners you guys use in chemistry lab, there's a hole on over here. The gas comes in at the bottom here. When the gas flows upward, so then there's velocity of the fluid inside here. So, and then outside air here usually do not have much speed, right? So inside have relatively larger speed, so then pressure inside will be smaller than the outside here. So then air will be pushed into the Bunsen burner to mix with the gas, okay? Also, if you have a perfume bottle, if you want to smell it, you usually kind of wave your hand at the top, right? All you can do with the squeeze bulb here, squeeze it, and then you will create airflow. So basically, you're creating airflow on the top here. So then the pressure over here is less than the pressure down here because there's no airflow here. So then the perfume will be pushed upward because of the pressure difference, okay? Similarly for other two here for the aspirator. So in the chemistry lab, you can have an aspirator that has water goes down, right? So then air will be sucked in here. For the chimney here, if hot air goes up, okay, so then the cold air will be picked up because there's airflow here, then pressure inside is smaller than the pressure outside, so the air will be pushed in. Okay, so just these are just a few applications in our daily life you can actually observe often. All right. Let's take a look a demo first, okay, before we actually solve for this problem. So let's do that. Let me just reshare my screen over here.
Before there were airplanes, before there were trains, there were sailboats. Without them, the world as we know it would not exist. Square-rigged sailboats brought Europeans to America. Their stable decks and massive holds carried the people and supplies that would build San Francisco. But these ships of old had their limitations. They were slow, and they only went in one basic direction, with the wind.
Square-rigged sailboats work by using sails as kind of more of a drag device than a lifting device, like a parachute.
A lot has changed. Today's sailboats apply very different principles to harness the power of wind and wave. So if you want to master modern sailboats, you'd better learn some physics.
So why did the wind shift? Just because?
The Quest team attempted to do just that on a recent sailing lesson at Modern Sailing Academy in Sausalito, California.
I think students, when they first come here, they know that the wind will push the boat because they see like a plastic bag being pushed across the street. So they can understand right away that the boat can be pushed, but what they have to learn is the boat can also go into the wind by using aerodynamics. Just like an airplane wing, the sail can lift the boat into the wind. So that allows us to go almost any direction we want to go, except for directly into the wind. Okay, hang on now, go straight. Go straight for just a second. You gotta get the boat and speed back up. Just go straight for a second.
So modern sailing's not all about being pushed by the wind. Something is happening at the sail that makes it fly like a wing. And that elusive something is a force called lift. To help us understand what lift is, we've brought in some heavy hitters from NASA Ames Research Center who just happen to be avid sailors.
We call it lift because of the analogy to an airplane wing, I think. Well, now in a sailboat, that's all turned up on end, right? So now what we think of as lift is really, in our normal frame of reference, is a side force.
I think a lot of people don't realize that they are exactly an airplane wing just stood up on its side. And granted, it's a floppy airplane wing, but it works the same. When you want to get geeky about it, you can really start looking down at the nitty-gritty and really start learning a lot about how the sail works.
And here's the nitty-gritty. It's called a water channel, and it's one of the best ways to study how wings and sails generate lift. In this channel, filled with moving water, streamlines of fluorescent dye are injected upstream of a test shape. Although air is a gas and water is a liquid, both are considered aerodynamically to be fluids, so the resulting virtual super slow-mo image actually shows us how air would travel along the length of a sail or wing.
Lights off. What I'm about to do is start introducing some glow-in-the-dark dye into the water. You notice that the streamlines on the lower side of the image are curving around the outside of the airfoil shape. Since those streamlines are curving, it has to accelerate a little bit. When it accelerates, it creates a lower pressure, and that's what actually generates the lift. And that lower pressure on the downside of the sail sucks the sail downwards to the bottom of the screen.
Essentially have high pressure on one side, and that higher pressure is trying to move toward the low pressure side and putting a pressure on the sail. That's from Bernoulli's law that says that the pressure forces and the velocity are related. You generate higher velocities on one side, so consequently there's lower pressure. Now you have the pressure difference, and that leads to the force.
Bernoulli's principle, named for 18th century Swiss mathematician Daniel Bernoulli, is pretty simple. Here's a way you can see it for yourself.
So I'm going to blow over a piece of paper that I'm holding in a curved shape, and we'll see what happens. So you can see how that lifts up. And that it completely relates to the flow acceleration over the curved shape and the fact that that higher velocity leads to lower pressure.
So as the wind travels along a sail, the sailboat's being lifted, or actually sucked, towards the curve of the sail, mostly to the side and slightly forward. But the wind generally hits the boat from the side, so why doesn't it just slip sideways? Because sailboats have wings above and below the water.
A sailboat, like anything dynamical, exists in sort of a balance of forces. The sail's above the water acting as a wing, and the majority of the lift that they're producing is in a sideways direction to the boat. Only a small component of that lift force is actually angled forward. Now, under the water, there's a keel, and as you move through the water, it's also developing lift. Its lift is predominantly sideways also.
In a modern sailboat, the keel and sail work together to move the boat forward. It's kind of like squeezing a watermelon seed between your fingers. Your fingers put equal sideways pressure on both sides, but the seed still shoots out in a forward direction. In a sailboat, the sail and keel's sideways forces cancel each other out, leaving only the forward force. That squeezes the boat forward, and bam, we're sailing. But as any novice sailor will tell you, it's harder than it sounds.
And in physics, they say you have a vector this way, you have a vector that way, and you have a resultant vector, which is the direction in which we are going.
It's tricky stuff.
It's tricky stuff, but it's fun. Because now
Okay, so we've captured the wind, and we're zipping along in the direction of our resultant vector. And that's all there is to it, right? Not so much. An experienced sailor knows that fine adjustments to the curvature of the sail, called trimming.
All right, I think we'll just stop here. That should be enough for our content here. All right, so let's go back to the slides over here. Let's take a look on this problem. So it says calculate the approximate force on a square meter of the sail given the horizontal velocity of the wing is 6 meters parallel to its front surface and 3.5 meters per second along its back surface. Take the density for the air to be 1.29 kilogram meters cube. So this should be, you should be using the Bernoulli's principle. Okay, so P1 or P front plus 1/2 rho V front squared is going to be equal to P back plus 1/2 rho V back squared. Okay. And then it's asking you to calculate the force on a square meter. So it's force per unit area. So that means you're actually looking for the pressure difference, okay, between the front and the back. So the back will have a larger pressure. So you're actually looking for P back minus P front in this case, okay? What would that be? So I can give you again a couple of minutes. You can work on this and then we'll be looking at the solution together, okay? All right, I think we can take a look here together. So we can write it up that we can put the back on the left hand side. So P back plus 1/2 rho V back square should be equal to P front plus 1/2 rho V front square. Okay, because we are looking for P back minus P front. That's why I put P back on the left and P front on the right hand side. So I'm going to move this guy over here and then this guy over there. Okay, so you'll have P back then minus P front on the left hand side. That should equal to 1/2 rho V front square minus 1/2 rho V back square. Okay, you can single out the common terms 1/2 and rho. So then V front square minus V back square. Okay, now plug in the numbers 1.29 for the rho, and then the V front in this case would be 6.00 meters per second square minus V back, which is 3.50 meters per second squared. Okay, so remember on the velocity terms, you want to square them. Okay, that will give you a larger difference actually. So that would be 15.3 meters or newtons per meter square. Okay, so that would be the force on a square meter on the cell. So each square meter of the cell will give you 15.3 newtons of force. Okay, and then that's mostly on the sideways. Okay, as explained in the video there. All right, again, I'll pause for a few seconds to see if you guys have any question and before we move on. Okay. All right, so if you are clear, we'll move on here. Some more applications of Bernoulli's equation. So for the water dam, actually, you need a dam because you actually need a relative higher speed of the water coming out of the dam over here. So this you can apply Bernoulli's principle here as well, or Bernoulli's equation. So then the velocity at the bottom here will be like the same as if you have something drops through a distance of h. Okay. All right. Let's examine the terms in Bernoulli's equation here. So on the left-hand side, or on the one side of the equation, you have P plus 1/2 rho V squared plus rho GH, right? We can take a look on the second term here, 1/2 rho V squared. Okay. Rho is equal to mass divided by volume. So this is equal to 1/2 mass V squared divided by volume. Okay. So then this is over here 1/2 m excuse me mv squared. This is the energy, right? Kinetic energy. And then if you have energy divided by volume, so that will give you energy per unit volume. So that means energy density. Okay, so this has dimension of energy divided by volume, or E over V. Similarly, you can examine this term over here, rho GH. So rho again will be M divided by V. So mgh divided by V. Mgh we know as the gravitational potential energy. So it's energy divided by V. Okay. So then in that sense, this should be also, the pressure should be also having the dimension of energy divided by V. Okay, which is also true because this is equal to, pressure is equal to F divided by area, right? So then if you do the distance, multiply P with distance, our force, or let me just write on the paper here. So you will see what I'm talking about. So pressure is equal to F divided by area, right? So if you multiply both the numerator and denominator by D, on the top here, this is equal to work, right? F times distance will be giving work. On the bottom here will be volume. Work is equivalent to energy, right? So because work done will increase energy. So then the P also has a dimension of the energy over V. So these three terms all have the dimension of E, the energy over V, okay? So then if we multiply those terms with V divided by T, volume divided by T, then V and V will cancel out, right? Then you will end up with E over T, the energy divided by time T, okay? The energy or the energy is equivalent to power or equivalent to work. So then this is equivalent to work divided by T, right? So that will give you power, right? If you do energy or work divided by T, then it's equal to power, okay? So then Bernoulli's equation, in Bernoulli's equation, actually, both sides of the equation, it gives you power, right? So then that means if you calculate, or if actually it's not power itself, but if you multiply both sides of the equation by V over T, which happens to be the flow rate Q, right? So if you multiply both sides by Q, then it will give you power for the fluid, okay? So for the fluid, power in the fluid, then it will be P plus 1/2 rho V squared plus rho GH times Q, the flow rate, okay? With that, let's take a look on the power of the heart. Okay, so our heart actually has a power. So so this says the left ventricle of a resting adult's heart pumps blood at a flow rate of 83 0.0 centimeter cube per second, increasing its pressure by 110 millimeter mercury. So this is a unit for pressure. That should be in the last chapter. Its speed increased from 0 to 30.0 meters per second, and its height increased by 5.00 meters centimeters. Calculate the total power output of the left ventricle. Note the most of the power is used to increase blood pressure. Use density of blood as 1050 kilogram meters cube, and 1 millimeter mercury is equivalent to 133.3 Pascal. That's the unit for SI unit for pressure. Okay. So I'll just give you guys a couple of minutes and then we can take a look on the solution together. Okay. So basically you'll be applying to calculate power, you'll be applying the equation in the previous slide. Okay. Or the equation P plus 1/2 rho V squared plus rho GH times Q. Q is the flow rate. Okay. This is a flow rate. That will give you the power of your heart. Okay. I think I was muted. So here's the solution. So basically, you just plug in the numbers, but you want to be careful about the units. Okay. So pressure is given as 110 millimeter mercury. So you convert it into Pascal. Pascal is the SI unit. And then rho is already in SI unit given. Speed is not, you convert it into meters per second, the SI unit. And then the height h is not in SI unit. So you also convert it into meters, okay? The flow rate is not in SI unit. You convert into meters cube per second. So basically times 10 to the minus 6. So all these numbers, if you put them in the calculator correctly, it will give you just 1.26 in watts. Okay, that's the power of your heart. Okay. And you can let me know if you have questions. I will pause for a few seconds here. All right, if we are clear, we'll move on here on viscosity and lamellar flow. Okay, so we all know that different fluid have like thickness. Some is thin, some is thicker. So for example, honey is thicker, right? It's sticky. Water is not. So this is referred to viscosity. So honey will have more viscosity than water. Okay. So for lamellar flow, basically, if you have turbulence of the, say, smoke comes out here, so it's an air type of air, so it's also fluid. Okay, so if it just go in one direction, then the flow is called lamellar flow. If it curled and coming back, then that's called turbulence flow. Okay, so we just have to know the terminology here. Okay. All right, so for lamellar flow, the flow rate is defined by the pressure difference and divided by R, which is the resistance of that flow. Okay, so flow rate will be equal to pressure difference at two different points and divided by the resistance of the flow. So that resistance will include and all other factors. Okay. And if you look into detail of resistance, that should be equal to A times eta. Eta will be the viscosity of the fluid times L will be the length, and then pi r to the fourth, r will be the radius. Okay. All right. I think that's how much we need to know about this lamellar flow here. So the next section talk about molecular transportation. So in real scenario, actually, for the air molecule or fluid molecule to go from one place to the other place, so it actually doesn't go straight. Okay, so if it actually goes like from one point, from starting point over here, zigzag back and forth, back and forth, back and forth. Okay, so this is called diffusion. All right, the average distance can be calculated using this equation, square root of 2d capital D over T. Okay, again, we are not going into details of this. Okay, so I think that's how much you need to know about this section. Okay, so that will do it for this chapter and then also for today. Okay, so starting from Friday, we'll be checking on the last chapter of the semester here. Okay. So I'll stop here for today and then see you guys on Friday. Okay. Bye bye.